reinforcement learning. I assume you're already familiar with supervised learning, and let's start from there. In supervised learning, you make predictions. In reinforcement learning, you make decisions. And here's the difference. For predictions, there is an immediate ground truth. You can check the quality of your predictions versus the ground truth immediately. For example, an image is either of a cat or not. An email is either spam or not. See, these are predictions that you make on the input, and you can compare the output against the ground truth. In reinforcement learning, you make decisions, and the nature of the decisions is such that the outcome is delayed. So there wouldn't be an immediate feedback on whether you made the right decision or wrong decision. Instead, you make a sequence of decisions, and the quality of these decisions will become evident only at the end. The best example of this is chess, and I'm going to give you a whole bunch of examples of the use cases of reinforcement learning, and therefore what I mean by this sequential decision making and the delayed return or delayed outcome, if you like. In the game of chess, the first example, at your turn, you make a decision to move a piece, and there might be some indication on whether that was a good move or not, but the true indicator is at the very end when you win or lose the game, right? In Atari, let me zoom in a little bit. Okay. In Atari, at every moment, you have to decide whether to go left a little bit or to go to the right or speed up or slow down, right? And again, it may not be obvious whether that was a good decision, but you will know once you hit an enemy's target or whatever. Controlling drone or robotics in general falls into this category as well. Suppose your goal is to maintain the altitude and the location of a drone in the sky. Well, the wind current is changing, the engine vibration is impacting the position of this thing, and at each moment you have to decide on the settings of your drone in terms of the tilt or whatever, the engines. Again, that's another example of where you're making sequential decisions and the outcome is kind of delayed. A bunch of other examples that are less intuitive and yet very profound. I found them very interesting. One is controlling traffic lights. Say your goal is to use reinforcement learning to minimize traffic congestion in a city. So right now what you have are these traffic lights that are controlled by timers. They switch from green to red based on pre-programmed times. Say you wanted to use reinforcement learning to make a decision every second on whether a light should be red or green. And again, every time you make that decision, it's not clear whether that was a good decision. But then you can, at the end of the day, you can look at some indicators of traffic in the city, and you can tell whether that was a good set of decisions you made or not. Next example is relevant to Uber, Lyft, or other ride-hailing services. Well, they need to match riders to drivers. And on the surface, it may look like supervised learning might be a good way of doing this. You want to maximize whatever, and then you just map the rider to the driver, and that's it. But it's actually more sequential decision making. And I'm going to give you a hint of that. When you assign a driver to a rider, not only you are making that trip happen and that business to come true, but also you are making the driver end up at a different part of the city in half an hour from now. In other words, you're changing the layout of your supply and demand by making these decisions. And it's only at the end of the day when you can tell whether these decisions were good. So, for example, if you take a driver and through the trip take him to a part of town where there is no demand, well, that was a bad decision. Whereas another trip that on the surface may not look like such a good trip, but it drops off the rider in a dense region with a lot of demand, turns out to be a better decision. I have two final examples, and all of these are to motivate you on how vast the applications of reinforcement learning are, but also to show you the core characteristics of what the applications of reinforcement learning are. The next one is movie recommendation. So again, on the surface, you could build a supervised learning model to predict which movie you're gonna you're gonna watch, and then recommend that. But if you think more deeply about it, you're essentially making a sequence of decisions with a long-term goal in mind. And here's the example of this. Say there is a movie, and then there is the first episode of a TV series that you could recommend. Well, obviously, that TV series is a better choice for Netflix because that will hook you in for 5 or 8 seasons, whereas the movie is a one-off thing. Similarly, if you think about product recommendations on Amazon, if they could recommend a pair of sunglasses or a pair of rock climbing shoes, supervised learning may not see a difference. In both cases, it's predicting whether you're going to buy it or not. But reinforcement learning is more long-term thinking. It's thinking about the next action and the next action. And it may decide that a pair of rock climbing shoes is a better item to recommend, because once they recommend that and they buy it, now there is a whole bunch of other rock climbing supplies that they could start recommending to you. Whereas the pair of sunglasses was a one-off thing. It's a dead end. It doesn't go anywhere. All right. And the last example I have here is for online ads on Google or Facebook. So there's this concept of ad bidding, where Nike's, Adidas, other advertisers bid on an ad, on the placement of an ad. So when you go to your Facebook profile, the ad that shows up, well, there were a whole bunch of vendors or retailers that competed and bidded on that, and the one who bid the highest was placed up there. Now, as an advertiser, you put a budget of, let's say, $100 for a whole week to spend on these ads. And again, your goal is that by the end of that week, you have made the most business out of that money. It's not just this next transaction or next ad that will be profitable, but thinking more long term, right? Now, if I zoom out and look at all these applications, they are very different, but you will find there are two characteristics that keep repeating themselves. One is that the true outcome is delayed, it's not immediate. And the second one is dynamic environment. These decisions that you make along the way, they change the environment, they change the landscape. You're not looking at a static domain, but rather something that changes. Again, if I compare it to supervised learning, an email is either a spam or not. It has no impact on the other emails. An image is either cat or dog, has no impact on the nature of other images. I guess nothing is more obvious than the example of chess, where you make a decision to move a piece. Well, now you're looking at a different layout, and the next step, next action, constantly will change this layout, right? So these are two important characteristics of reinforcement learning applications. Now let's formulate a reinforcement learning problem, because on the surface these applications are very different, but once we formulate them, you'll realize that you can use the same methodology to tackle all of them quite similarly. So there are 4 components of reinforcement learning that you need to be familiar with. You have agent, you have environment, action, and state. Environment means the outside world. The agent is this piece of software, is the reinforcement learning algorithm inside of it that decides what to do. So it perceives the environment, it makes an observation of the environment, and it decides to take an action, right? state is a time snapshot of the environment. It's the observation of the environment that is fed into the agent, and the actions is how the environment alters the environment. Let me show you an example of a reinforcement learning application and what each of these components are. That's the game of Pong, where green is the reinforcement learning agent playing against a piece of software, which is Atari on the left. And your goal is to win the game, to score the ball. The environment is the game. The state is an observation of this game at one time snapshot. That could be in one moment in time. And the elements of that state could be like the position of the paddles, the speed of the ball, the location of the ball, the direction of the ball, that sort of things. The actions the agent can take are one of the three. You can either go up, go down, or stay where you are. The agent is comprised of a neural net. We'll talk more about it. That ingests the current observation of the game, and that could actually be the image directly of the game in this case. The state or the observation here is the image, and there are three output nodes of the neural net, one per action: up, stay, or down. And once you train the model, it will give higher probability of going up if it's the best thing to do to go up a little bit and others. And based on these probabilities, based on the numbers that the neural net is outputting, you will pick an action. So if up has a probability of 0.9, well, most likely you're going to pick up and take an up step. And now the game in the next time step will be a little different. The thing that I want to actually take you back to is that in this picture, you're looking at a cycle. You make an observation of the environment, pick an action, take that action, and now do the whole thing again. So it's more like what you see here on the left. At time 0, there is a state, take an action, the action at time 0, and then that turned the environment into time 1, and now you have a state from time 1, and then you take an action in time 1, and this goes on and on, right? So it's a loop that repeats in every time step. So when I talk about time step, this is what it looks like. So at time 0, this could be the state, and then next time step, next time step, next time step, and you can see the ball is moving upward, and at this time the agent is deciding to also move up, and now it's going down. So what you see here in every time step, the agent is making a decision on what to do. Based on that, takes the action, and now the environment is a little bit different from the moment before. Now that you understand what kind of problems reinforcement learning solves for and what that solution generally looks like, which is this whole paradigm of having the environment, agent, action, and states, next, let's talk about how you can train this neural net, this reinforcement learning model, to make predictions about these actions such that you would win the game.